Hello, my name is Nevo. I'm the CTO of cPacket. This video is part of our solution overview video series, and today we're going to talk about electronic trading or observability for electronic trading systems. The electronic trading ecosystem is one of the most demanding systems to run networks in. It's a combination of being able to maintain very, very low latency that many times is measured in nanoseconds, which implies that you have to build the network based on switches and routers and anything in between that is low latency, which implies, again, very small buffers. So there isn't very big buffers to be able to accommodate issues in the network. At the same time, as we say, every packet counts. Every packet carries multiple messages, one or more messages from the exchange, market data. This market data is being used by algorithms. And if any packet is missing and they're missing messages, that implies that the wrong decisions are being made, trades cannot happen, or the wrong trades happen, which implies that you're going to lose money. So an environment where operating the network is quite hard. At cPacket, we've been working with our customers in the electronic trading system for a while, for the last 12 years or so. The most demanding, both on the exchange side, so the sources of the data, as well as the high-frequency traders that consume the data, and anything in between. So the service providers in the middle and the traders at the end. And the fundamental thing that they're looking from us to provide is the ability to do things at use packets. It's passive. You're not able to add any more latency in the network, to be very precise at the performance that the network is running, all the way up to 100 gigabits per second today. In order to achieve that, we've developed over the years a complete solution. The solution itself is composed of multiple products. We have what will be considered a packet broker. The packet broker is quite different in the sense that it's not only used as a packet broker because of our ASIC and FPGA IP that we embed in every single port. We are able to extract a lot of metrics and understanding of what's going on at the port level and understand in very high accuracy what is happening at the network. So the first layer is the layer of packet delivery, the packet brokering, and packet analytics. The second layer is the ability to capture packets, lossless packet capture up to and including 200 gigabits per second, where at the same time extract the second level of analytics that requires things like understanding latency, understanding jitter, and things that you have to be able to capture packets along or over multiple seconds in order to be able to understand what's going on. And at the last part is our unified visualization or unified configuration command and control that allows us to visualize the metrics, allow the user, even though the products themselves are deployed in many, many locations over the network and in some cases over the world, being able to go to just one location to understand what's going on. As we'll talk later, you'll see that from the users, at the end of the day, there are kind of three fundamental use cases that, and when I say user, I mean the network operation team, they use our products and our, the different parts of the solution to address. First and foremost is the ability to root cause cases where people complain about packet or messages drops and or latency. In general, when we say root cause, we mean that someone is able to answer the 4 Ws, what happened, when did it happen, where did it happen in the network, and then understand why it happened in the network, if it is the network. And the packet drops, the important part when you're thinking about the electronic trading ecosystem is really about a single packet drop can cause issues, right? So it's really where every packet count. It's not about being able to address things where 70,000 read transmission in one session is not a big deal. And when we talk about latency, it's not that you are allowed to add 20 milliseconds of buffering. It's really about the ability to understand latency that changes within nanoseconds. The second workflow, or the second use case, is about being able to proactively perform capacity planning. Many of these networks are global networks and require wide area WAN links. WAN links take a long time to procure, somewhere between a quarter and 2 quarters. They're expensive. And the SLA that you have to deliver on them is not just the average consumption, but really the microburst consumption of the bandwidth. So only by understanding the real consumption of bandwidth, looking at sub-second resolution, looking at microburst resolution allows you to be able to plan ahead, as well as being able to understand which stream across the link is the one that is consuming the bandwidth. And last but not least is the ability to meet tight SLAs, right? So if you're a service provider of electronic trading or an exchange and you have multiple subscribers, the SLA that they expect is something that can meet microbursts or essentially lossless packet delivery and latency that is measured in nanoseconds, as well as being able to meet compliance requirements that, again, can be measured in very accurate. So when we talk about fairness between exchange and alternate exchanges, you have to be able to prove that you provide a fair treatment within nanoseconds many times. So the solution overall has multiple components. The most fundamental and the foundation for everything that you do when you think about observability for electronic trading, ultra-low latency or low latency trading is about timestamping. You have to be able to understand as accurate as possible when a packet arrived at any monitoring point along your network. You want to be able to timestamp it very close to the port. You want to be able to timestamp it as in nanosecond accuracy, and you want to be able to do it for all the packets. The way we achieve that is essentially by creating a packet brokering that is quite unique. So the architecture that cPacket uses implies that every single port in our packet brokering devices, the CVU-NG, have a dedicated ASIC and FPGA for the port. So what you're seeing here is a general architecture of the packet broker. You can see the smart ports on the ingress side. You can see smart ports on the egress side. In between, we're using a switch such that you can deliver packets from any port to any port. But once we double-click and look at one of these ports, they perform quite a lot of functionality. First, and again and foremost, is the ability to timestamp. We timestamp the first symbol of the packet as it arrives at the port. So the only latency, practically the only latency that you have between the timestamp we provide and the timestamp that is seen at the port, at the switch level, the switch port, is the length of the tap, which can be somewhere around 4 to 5 to 8 nanoseconds. So we're really talking about accuracy within minimum number of nanoseconds. That timestamp is being added to the packet and as a trailer, and everything that is done down the road, whether it's our devices or our tools or any other tool, can leverage this timestamp to understand the actual timing of things along the network. The second part of the solution is really understanding bursts, right? So when you are dealing with ultra low latency network and which implies very switches with very little memory, it's enough to have a very short burst and which will cause you packet drops, right? So while other solutions that may try and understand what's going on at the switch will use essentially switch counters that are very low resolution, not very accurate, which makes it very hard to understand the burst or the microburst level. On the other hand, what we do at cPacket, we allocated FPGA resources such that we sample or we calculate the exact number of packets that is going through the port every millisecond. So these type of counters, the 1 millisecond counters, allow us to understand bursts and not only detect them and not only show when they happen during the time, but also allow you to see which workload caused the burst, right? So what we would call microburst analysis beyond microburst detection. The next level of analytics or analysis really requires a next level of product. So beyond the packet broker that is able to do things at real time and inspect and timestamp every single packet, calculate things, calculate bursts at very high scale. So we can do burst analysis on our packet brokers and use something like do it at 1.6 terabit per second or 3.2 terabit per second. The next level where you want to understand sequence errors, you want to understand latency, we leverage our packet capture and analytics. So the way we perform that in our packet capture analytics, the cStor devices, is by capturing the packets and writing them to disk up to 200 gigabits per second, while at the same time, before writing them to the drive, we perform the analytics and extract all the metrics, indexing, and information that is required to understand the next level protocols. And the first protocol that is relevant in electronic trading is really about market feeds, right? Market data feeds. So market data feeds are delivered over IP multicast. There are no retransmissions. They flow down the ecosystem. And again, it's very sensitive to every packet. Every packet counts. So any packet drop will cause a message drop. There's one or more messages, which will give the algorithm the wrong information or not enough information to perform the trading, right? So we are able to inspect these at real time, extract the sequence number, whether it's a sequence number of the message or the packet, and identify any missing packet, missing messages, and or in more rare cases, packets out of order if something is wrong in your network. So sequence issues or duplicates or anything that is going wrong with the sequencing of packets as they flow down the path. The other component is the ability to understand latency, right? So the two issues that you have to deal with when you deal with market feeds is packet drops on one hand, latency issues on the other hand. And latency, there are two parts of that. One is one-way latency. So if you have a stream and for whatever reason, one of the entities along the path introduces more latency than expected, and or jitter. You want the packets to arrive at the time that they were sent, right? So you don't want to see delay variations along the path. So we are able, again, using the hardware timestamp that we have versus the application timestamp on the other hand, to keep track of the latency and the jitter and identify issues that will cause your customers or will cause your consumers of the data to be unhappy. Next level of protocol decoding is really about multicast, understanding the multicast trees. So market feeds are multicast by and large, which implies that all the way from the traders, you have to join, leave, and so forth, the tree You don't want people to subscribe to too much. You don't want people to subscribe to too little, and understand if you have any signaling issues that cause people not to receive the data they expect. So we're able to extract all the multicast messages, whether it's PIM and IGMP, extract the joins, extract the information, and be able to give you a join tree such that you can understand in real time, or scroll back to the time that someone complained and understand if there was a signaling issue that caused them not to receive the information they were asking for. One more component, which is really about when you start going beyond the market feed, right? So if you're thinking about the tick to trade, then the other component is, of course, the TCP sessions and the ability to execute trades which carry over TCP, and they carry their own path. And what you want to be able to understand is if someone is complaining about latency, was it a server overload, or was it a latency that happened along the path? So in this simple example, you can see that, if everything is good in the nominal case, the latency before and after this middle box that we named here a load balancer is low, which everybody is happy. In the case that you have a network issue, so the middle box, the load balancer, is getting overloaded, you'll see that the latency between the load balancer and the application server or the trading server remains low, but the latency as measured between the client and the load balancer is all of a sudden getting high. On the other hand, if it was an application issue and not a network issue, both latencies will go up at the same time, which means it's not a network issue, but rather it's an application issue. Lastly, and this is where the interface between network operations and the users, the people that develop the traders or the algorithm developers meet many times, is the ability to say, okay, after we ran for a day and we want to test our algorithms, we want to test our infrastructure, we want to test a new algorithm, can you replay for me what was captured yesterday? And we're able to use the capture, our packet capture, to replay the data so you can run in production, receive the data, and then off hours or the day after, replay the exact same stream at the same speed or faster or slower, and test or validate the algorithms on the other, on the other side. So just to put it all together, right, we talked about quite a few features, and they all fit together. They're somewhat distributed in implementation, right? We have the timestamping microburst analysis that we leverage our packet brokering. We have the ability to capture without loss, perform market data analytics, multicast analytics at our packet capture. And then at the top, the ability to visualize, understand what's going on in your network, perform the hop-by-hop analysis, and or create alerts and notification if something goes wrong. So the next thing we're going to do is go for a demonstration. The demonstration will stay within the cClear and the dashboards, and then that will help you to understand how things manifest themselves for the user. So for the demonstration, we're going to use cClear. So to remind you, everyone, cClear is the one device/application that we use to control and manage all of our estate, as well as being able to collect metrics and visualize them. There are multiple videos that explain how to use cClear, so I'm going to skip that part, and I'm going to jump right into some of the dashboards that collect the information that I was just talking about. So, as I said, all the analytics that we do kind of assumes that we have the timestamp, the hardware timestamp, and then all the other calculations and all the other analytics that we perform count on them. So the first thing that we mentioned is the ability to understand microbursts. So when you think about microbursts at the port level, is really the idea to understand what is the behavior of the port when you go into a much lower resolution of throughput than the normal one. So every second, CVU sends, or our packet broker sends for every single port the throughput as it sees that on over a second. And in this case, I'm looking in one port in our lab, and I can see this is a 10 gigabits per second port. And when I measure over 1 second resolution, it doesn't go much higher than 1 gigabit per second. The other capability that we have and that we use to understand cBurst, or that we understand microburst, is the ability to also divide the second into 1,000 milliseconds and give me what was the max throughput in milliseconds during that second. And when I add that graph, you can see that all of a sudden, it's actually multiple times gets all the way to 10 gigabit per second. Right? So again, it's a port that it's 10 gigabits per second. If I look at the average, it seems fine. As soon as I add the 1 millisecond resolution, I can see that it runs at 10 gigabit per second. And actually, where you thought a burst happened when you look at the average is actually not the time that a real burst happened when you look at the port. So this is good. This is one way to understand microbursts or detect a microburst and can explain packet drops. But what you really want to understand is, certainly if you talk about streams of market data, is which stream is the one that caused the burst. So this is where our feature we call cBurst, or burst analytics, allows us to break the port into 1,000 filters or 256 streams and tell you for each one of these ports or each one of these streams on that port, what was the throughput when I measure it at 1 millisecond resolution. And you can easily see that there was very specific stream, in our case, a specific workload on this port that caused the burst, right? So now I can go and say, okay, I can rebalance the stream, I can send it to a different device, right? There are multiple actions that I can take once I understand what the source of the burst was. One more quite important information is that not only can I tell you in 1 millisecond resolution what was the source of the burst, I can also tell you how long a burst was during this time. So because if you only look at the max and it was only 1 or 2 milliseconds, it might not be a big deal. But if it is like in this case, which is actually 800 milliseconds out of a second, the burst was running, that's a much more significant issue than just telling you that the max was 10 gigabits per second. So this is the ability to understand burst, right? So microburst analysis. The next level is the ability to understand market data. And again, as I mentioned, on market data, we're able to decode multiple protocols today, specific protocols. Usually, these are protocols that we see running at very high speeds, which is harder to do in offline decoders. And I'm able to see, in this case, it's Impact or Opera. I can see the multicast group, destination port, and the specific VLAN. So you can think about the VLAN essentially as the monitoring point. In the case of Impact, you can see that I'm monitoring it in 2 different locations in my network. It's all a replay, but I'm replaying it in 2 locations. And you can see that the sequence errors are actually different, which means that there is an additional entity inside my network that introduces even more sequence errors, more gaps, duplicates, and so forth, right? So this type of information, you can understand the packet or the missing packets or the missing messages is something you can see not only for the stream, but you can also pinpoint where in the network the problem occurred. Now, this is our lab, and obviously we introduced the gaps. It's not in production. I don't think you want to see that in production, but I hope you understand the concept. And the other side of things is really latency, right? So it's like, okay, this is the how many packets I saw, this is still the visualization of the gaps, right? When did the gaps happen? So I can zoom in and understand exactly where it happened. But more importantly, in addition, I'm able to understand the average transit time, so along the path. So we basically compare the application time to the hardware time that we have. So you can see that it's about 7.4 millisecond for this specific protocol. And we're also able to look at the delay variation, so the jitter, so right, which implies that you have, in addition to the fundamental latency, you also have buffering that causes the stream to change latency. The next is about understanding multicast. So we are able to track the multicast stream. So you can say how many packets for each one of these stream went through the network. You can obviously, again, map it if you wanted to the monitoring point based on VLANs. But the more important thing is the ability to keep track of which clients joined us to join the stream, right? So if somebody is complaining that he doesn't receive the data, but you can keep this Sankey diagram, you can keep this tree distribution such that you see if it asked to join or didn't ask to join, which helps to root cause cases where people are complaining that they did not receive any of the data. The last part that we talked about is understanding latency. Again, latency for more of an application. We talked about one-way latency for multicast streams in the context of market data. When you talk about trading, they will run many times over TCP. And you want to understand where was the latency introduced by one of the devices in the network, or was the latency introduced by a case of a server overload. What you're seeing here is again, it's a simulation or emulation in our lab. We created an environment where you have a client and a server, a device in the middle that we'll call it a load balancer. And you can see two cases, right? One case here on the left, you can see that the latency at around, we'll look at the time, around 9:17, 11 a.m. Jumped. But the way that it jumped is such that the latency around the server didn't go very high. On the other hand, the latency on the other side of the load balancer jumped quite a lot, right? So that's a case where the entity that introduced the additional 5 milliseconds of latency is not so much the server, it's not really the server, but rather it was the load balancer, right? So that's usually the network team will have to go and resolve that. On the other hand, around 8, we see, again, a jump in the latency, but in this case, both monitoring points show the same increase in latency, which implies that the reason that the latency went up around this time was really a server overload. Nothing really changed at the network. So that was for the demonstration. We basically showed you all the components that we discussed about, right? All the use cases. So the ability to understand microbursts, ability to understand market feed gap and latency detection, and multicast and latency, the way they are manifest themselves in dashboards on cClear. So to recap, for network teams that need observability in order to be able to quickly root cause the issue, and in order to root cause the issue, they have to be able to answer the 4 W's, right? What happened, when did it happen, where and why. We try to give you a quick understanding of the capabilities that we have at the cPacket solution, as well as how they manifest themselves in our dashboards. Thank you so much for watching. If you're interested in any more information, please feel free to go to our website and ask for someone to contact you.